In this video, I'm going to continue with the practice questions on topic 2, all about electric fields, and eventually we'll get on to Gauss's law. So starting off on 28, this is part 2, so we've already done the previous questions. On this one here, it says there's an electric field pointing upwards. Okay, so if this is pointing upwards, we already know it goes from plus to minus. Okay, you have to find out what we can conclude from this. The upper plate is positive, well that's wrong, we just figured that one out. A proton at X would experience the same force at Y. Well, actually, yeah, even Z. The force is a uniform field. A uniform field means F equals EQ. The distance or the location is not important. All I need to know is the field and the charge. This is the correct answer. It will not experience a greater force or a lesser force. The force is the same in this case. The electric field is the same. The force is the same. This next question, similar idea, pretty much the same thing, right enough. All we've got now is that we have it going from the positive to the negative like this, automatically ruling out this one. A greater force, wrong. Less force, wrong. Same force, correct. Uniform, same force. Over here, P is located here between two. Compared to the magnitude and direction of an electron, what can you talk about with the force? Now, this is going from plus to minus, and it is a uniform field. The force is the same, the magnitude is the same magnitude, wrong, wrong. So A or B, direction. If I had a positive charge, he will go down. But if I had a minus charge, he will go up. He's attracted to the plus, isn't he? So I will have opposite direction. B would be the answer over here. Alright, so a proton moves along the positive x-axis and enters an electric field directed along the positive y-axis. What does that mean? We have a proton going in the positive x-axis. This is x, positive is to the right. We can assume that right and up are both positive, and we will assume that down and left are both negative. Okay, this is the general convention for it. Okay, but the field is pointing along the positive y. Positive y means up, which means I have a field going upwards. A field is going upwards. That means on the bottom will be plus. There, I failed 3 times to do a plus. Oh my god, that's terrible. Let's try one more time. Oh my god, I'm so bad at drawing pluses. Why? Ah, there we go, nice. And then at the top must be minus. Ah, good, I can do a minus at least. Right, what will happen? Where will he go? Well, of course, he's a positive, so he'll be attracted. He will go up that way. That is not a field line, so I don't want you to get confused. This is the path. I'm going to draw the path with a different color, so let's get my pen back over here and choose a color. Let's try green. His path is going to go towards this way, like that, along the positive y-axis. So that means D would be the answer over here. We don't need to use any of the right-hand rule stuff, talking about the z-axis, that all comes later, not when it comes to simple things like this. Don't worry about that. Charge is placed at the center of a cube. What is the flux of the electric field through only one face of the cube? Not the whole cube, only one face. What does that mean? We have a cube. We know a cube has 6 sides. A cube should have 6 faces on it. This is my attempt at drawing a cube, and that's good enough. So what I've got here is a charge inside it. Let me change the color for the charge. I have a charge inside. The field lines come out in all directions. It doesn't matter where in the cube it is. It could be the center. It could be on the side of the cube. I can place it on the side. It doesn't matter. Same number of lines will be coming out each face. We already know the rule is for the flux, we can say Q over epsilon naught. That will be my total flux. But we have 6 sides. I want to know one side. So instead of that, I will do Q over 6 epsilon naught. I'm dividing it by 6. I'm going to do my answer, whatever my answer is, then I have to divide it by 6. So I can just write it here as well. So that will be B. All right. So moving on, we have a flat surface is rotated, and now you need to know the electric field when it is perpendicular, when the electric field is perpendicular to the surface. Now, many of you get confused when what's perpendicular, what's parallel. So let's quickly try to draw a surface out. Here is a surface, okay? It's pointing upwards, okay? This is a surface. Now, if I have a field passing through my surface, let's say my field is going like this. Let's say like that. Okay, now this field is perpendicular to the surface. It is also parallel to the normal, or the area vector, whatever you want to call it. The normal points out of every surface. So if I drew another surface like this, the normal will point outwards. Even down, doesn't matter. I've chosen up for now. Or I could have it at an angle. And there's my normal there. Same idea. Let's just say I take the same field, the same two arrows, and I pass through both of these. Look at that. Okay. You can kind of see that this catches the lines. This doesn't catch the lines. It is actually parallel to the field, which means the normal is perpendicular to the field. Okay. Over here, the angle should be between the field and the normal. This is my angle over here. All right. So when I do this, if I see this normal is going to be the same direction as the field. That angle, cos of 0, it's a dot product, so we use cos. Cos of 0 would be 1, which means full. That's perfect. This is good. So I will just do EA, the general rule, by the way. Flux equals EA. Flux equals EA. It is also Q over epsilon naught. That's only good if it's an enclosed charge. So this part we don't need right now. It is the EA part I'm looking for. EA cos theta. And here, theta, well, cos theta will just be 1, so I don't need to include it. Over here, what's this? Cos 90. Cos 90, well, that will just be 0, which makes sense, because I'm not catching any lines. So over here, I do not use a random angle at the side. No, it must be between the normal and the field line. This will be cos of something, I don't know, 30 for example, and you'll get your answer. So you will add the EA cos 30 in this case. That's a general rundown of the idea. So now let's get into this again. You have the surface area. It's in meters squared, so that's fine. You have the electric field, EA, very nice. Now we need to know when this is field being perpendicular to the surface. The field and the surface are perpendicular. That is cos of 0. The normal is in the same direction. If the field is perpendicular to the surface, it is parallel with the normal. So I will directly use EA. I will do 3.2 times 6.2 times 10 to the 2. And if you put that into your calculator, you should hopefully get D. 1.98 times 10 to the 6. Okay, so I just multiply these two numbers together. That's all. What about now? It says the field is parallel to the surface. The field is running parallel to the surface. That is cos 90, which is 0. No need to calculate anything. It'll just be 0. Okay. A cylinder is like this. The net flux, the total flux passing through. So it's coming in and out. Even if it's going straight, it's going to go in and out. It cuts in and out. What does that mean? There is a normal over here. There is a normal over here. So this is cos of 0, which is 1. This is cos of not 0 because it's an angle going like that. That's actually 180. Cos of 180 is minus 1. Even if there are slight angles, the angles will be opposite, and they'll all add up to, well, essentially 0. Minus 1 plus 1. No matter what the E is, or the A, or the Q, whatever it is, coming in equals coming out, they cancel each other. Plus 1 minus 1, 0. That's all you need to remember. If the charge is outside, the net flux is 0. If the field originates from outside, the net flux is 0. If the field originates from inside, then you do Q over epsilon naught. Okay. Now, these are lines covering some sort of charge. When is the flux not going to be 0? So I kind of half gave it away in the previous one. So as long as the charge or the field is enclosed, it will be a value. So look at that. I have an enclosed charge inside my ring. So that means this is going to give me a value. I've moved it off to the side. I actually mentioned earlier in a previous question, even if I put it to the side in the cube question, it doesn't matter. It still will come out in all directions. Look at this one over here. Field lines are coming in and out. They will cancel. Plus 1 minus 1. That is not going to happen. Same thing over here. In and out. They will cancel. Not going to happen. Same thing. In and out. Plus 1 minus 1. Cancel. Over here, in and out. Doesn't matter how strong it is. Each one of these ones will all cancel each other out. So that will be 0 as well. So 1 and 2 only. B is the answer over here. Here is a cube. Now we have an inward electric flux passing through one face and the electric flux passing to the outer face. And the fuel is outside. What is the, forget everything, it's asking you for what? What is asking for you? The flux, there are no flux lines passing through any of the face. If the magnitude of the field at the center of the cube is E, the total charge inside the cube, well, of course there's no charge inside the cube because you would have more field lines coming out than coming in, so that's not happening. So it must be 0 inside the cube. Okay, a charge is enclosed by a Gaussian sphere. Okay, so if the radius is doubled, what happens to the flux? Okay, so let's think about the formula now. We have two rules. Flux equals EA, or enclosed charge, Q enclosed over epsilon naught. You can see that the radius is actually not even in the formula, so you can kind of guess that it will not make a change at all. But let's understand why it remains the same. If I placed a charge here is my charge. Let's say it's a plus charge, a field line coming out, out, out in all directions, out like that, and I enclose it. Here is my radius. Let's say this is 1 meter. 1 meter. 1, 2, 3, 4, 5 lines coming out. My flux, let's pretend I'll call it 5. Okay, I'll do my thing. It's called 5 Webers. By the way, the unit for flux is Webers. Fine. What if I increase my radius? Let's make radius bigger. Radius is bigger now. It's a terribly drawn radius, but that's actually so bad. Can I cancel that? Okay, let's try that one. Oh my god. Let's try that one more time. That is a little bit better. Why are you not clicking anymore? Thank you. Now, let's make that radius double. How many lines are passing? 1, 2, 3, 4, 5. My radius has become 2 meters, and I have the same number of lines passing. So it's a number of lines passing through an area. That is what the flux means. The definition of the word flux, number of lines passing through an area. So this is also going to be 5 Webers. The radius does not make a difference. Okay, so that's kind of like a trick question. Fine. Moving on, what do we have here? We have a cube, and look at that. We have the field outside passing through straight away. No need to do any calculations. This is going to be -1. This will be positive. This will just cancel each other out. There is nothing inside. Over here, same question as before, but written in a ratio format. I already said to you, it does not matter how big the radius is. This line is passing through both radiuses. This line will pass through both radiuses, or radii, if you want to be specific. That is the same. So the flux is 1 to 1. It's 1 over 1 equals 1. There is not double or quadruple or half. It is the same. All right. In order to use Gauss's law, we must know that, so Gauss's law only really works in symmetrical objects. If you've really noticed that we're using cubes, we're using spheres, we're using cylinders, so it must be symmetry. Your answer must mention something about symmetry. So I see the word symmetry here, so that means it must have a high degree of symmetry, which basically means it must be symmetrical. So D directly, I have the answer. So now, in these Gaussian surfaces, we want to know a net electric flux. I want the flux to be, the rule is Q over E. I want the final flux to be plus Q over E, just a single Q only. So let's have a look at all of them. Let's start with A. A is the whole enclosed flux. So I only count my enclosed charge, which is all of them, plus 3 minus 2, which is plus 1. Minus again, which is -1, and that will take me to 0, sorry. So plus 3 minus 2 minus 1 takes me to 0, plus 2 takes me back to positive 2. So actually all you can do is just stick it in your calculator. You will write plus 3 minus 2 minus 1 plus 2 equals 2. So that equals to 2, and that is not good. A is not good. Let's continue, because we want the final answer to be positive Q. We want it to just be 1, basically. I can kind of maybe already see it, but let's continue. Let's look at B. Looking at B right now, I'm going to do it here, and I'll have only the enclosed charge is all I care about. That I have a now enclosed for B. This is the shape for B. Plus 3 minus 2, plus 3 minus 2, of course, is 1. That's exactly what I need. This will be here. B is the answer. Let's just make sure that there are no other answers. Make sure there's no other mistakes being made. Let's look at C. Here is C. This is the shape for C, badly outlined. Minus 2 plus 2 is 0. Okay, so that's not going to be positive Q. That's 0. So the question might ask you, by the way, which of them will have a 0 overall. Looking at D, I have minus 2 only. That's minus 2. Nothing else enclosed. These charges will come in and out. They will cancel each other out. They will cancel themselves out, basically. Only enclosed charge is -2, not possible. And of course, E is -1. I can see that right here, that's -1. That we already know that's wrong. B is the answer. I hope that makes sense. Which has no electric flux? Then I just gave away it. Yeah, I just gave it away in the previous question. I said which of them will have no flux, which basically means 0. And I mentioned that when we did C. -2 plus 2 is 0. So the answer for that one is C already. Okay. I'm going to stop that there because this is getting quite lengthy. I'll continue in the next video.